Let's talk about the comparison tests. So these are just more tests, and we're going to learn even more after this, that can tell you whether a series converges or diverges. So we're going to learn two of them. The first one's the limit comparison test, but both of them are about series that have positive terms. So we're going to assume that a sub n and b sub n are always positive. And also suppose that if I do the limit of a sub n over b sub n as n goes to infinity, that I get a finite and positive answer. So c isn't zero, it's not infinity, and this limit exists. So we get a finite positive limit. That means that these two series do the same thing. So the series with a sub n in it and the series with b sub n in it, either they both converge or they both diverge. And by the way, when I write this, I'm not writing like n equals 0 to infinity or anything, because I want to be a bit vague about that. Remember, we went over the fact that it doesn't, if we're talking about an infinite series, it doesn't really matter where n starts. If all we want to know is whether the series converges or diverges, n could start at 1 or 2 or 10 or wherever, and that has no effect on whether the series converges or diverges. And that's what this is all about. All we're saying is whether a series converges or diverges. So I just went ahead and left that information off. So this is supposed to be a sum from n equals somewhere to infinity. It doesn't matter where it starts, and likewise for this. So of course this is called a comparison test because in a sense, we're comparing two series. We've got a sub n and b sub n. Anyway, let's use this for something. So here's a classic limit comparison test. We're going to learn to look at something like this and immediately see that the limit comparison test is a good idea, but this is our first time. So what I'm going to do, I'm going to have two sequences, a sub n and b sub n, and one of them is just going to be the one that's given. So usually I just let that be a sub n. The other one, we get to make up whatever we like, pretty much. Of course, we'd better make up something that satisfies this, and we better make up something that has positive terms, otherwise we're not allowed to use the limit comparison test, but we have a lot of choices here. So here's how to make a good choice. Basically, I'm going to look at a sub n and ignore what I'm going to call the unimportant parts. And the important parts are the big parts. What I'm thinking of n as a big number. So I'm looking at the top of the fraction, and I would say that the 3 is a lot less important than the 2n, because if n is a huge number, the 2n is way bigger. On the bottom, I'm just going to keep the n cubed and drop everything off. So really, you could say I'm just keeping the leading terms. This is a good strategy if you're dealing with a polynomial over another polynomial. Just keep the leading terms. Your b sub n should be a lot simpler than your a sub n. In fact, we can even simplify this. 2 over n squared. Okay, so that's my strategy for picking a b sub n. And I guess, yeah, if I'm being careful, I should just write down something just checking that a sub n and b sub n are positive. They are, as long as I'm plugging in something from 1 to infinity. The top is a positive number, the bottom's a positive number. Also, if I look at b sub n, I've got 2 over a positive number, so I'm happy with that. What's going to take a little more work is this part. So I'm going to do the limit as n goes to infinity of this over this. Okay, so I've got, here's my a sub n. and I'm dividing it by my b sub n. Okay, I've got a fraction over a fraction. So I flip the bottom. Let's multiply through. And from here, there's a number of things we could do. We could use L'Hopital's rule, for example, because this is infinity over infinity. I'm going to go ahead and use the shortcut where if the top is a polynomial and the bottom is a polynomial and n is going to infinity, all that matters is the leading terms. The leading term on top and the leading term on bottom. So it's like I can just cover this up with my fingers and I can see I'm going to get 1. So let me show a little bit of work here. But I'm just using the shortcut. All that matters is the leading terms. And of course these cancel. I just get 1. Okay, so where does that leave us? We were running through just checking what the stuff that we need to check to apply the limit comparison test. And we just did this, and we got this limit to be 1, which sure enough, that's a positive finite number. So what does that tell us? That tells us that our two series, the series with a sub n in it, which is this series, and the series with b sub n in it, they both do the same thing, whether it's converge or diverge. So let's investigate this series, and I'm just going to start it at 1 because this starts at 1. And again, like I said, for the questions that we're asking ourselves, it doesn't matter where n starts. I could start it at 2 or 10 or whatever. But the question is, does this converge or diverge? So I look at this, and now my life is a lot easier because this is a much simpler sequence, or a series, I meant. And in fact, this is a p-series. Well, it has a 2 on the top, so technically I guess it's 2 times a p-series, because a p-series is supposed to be 1 over n to the p. But this is another thing that we discussed. A constant multiple like this 2 doesn't have any effect on convergence or divergence. In fact, I could pull the 2 outside of the series and just put a 1 on top. I'm not going to do that because it doesn't matter. So, yeah, this 2 doesn't affect us, like this 2 on the top. The important number is the power of n. So this is like a p-series with p equals 2. And we recently learned that a p-series converges as long as p is greater than 1. So the series with b sub n in it converges, therefore our original series, this one, also converges. Okay, that's how we do it. Let's talk about the other comparison test, the direct comparison test. So this one certainly has its place. It is important. I should tell you that overall, you're probably going to find yourself using this one less often than the limit comparison test. And maybe I'll get into the reasons for that after I explain it. So for this one, we have two series. There's an a sub n and a b sub n. and we're going to impose an inequality between them. So let's say that a sub n is greater than or equal to b sub n, and they're both positive still. But both of these tests that we're learning are about positive terms. So they're positive, and a sub n is greater than or equal to b sub n. So there's two ways to use this. If the series with b sub n in it diverges, then the series with a sub n also diverges. The other way is if the series with a sub n converges, then the series with b sub n converges. The way I think of this is when we're talking about series with positive terms, what it means to diverge is that basically you're adding positive numbers and you're going forever, and diverge basically means that it gets too big. As we go, we keep adding these positive numbers, the sum gets larger and larger, and it goes to infinity. That's what it means for such a series to diverge. For such a series to converge, that means that even though we're adding positive numbers as we go, these positive numbers are getting so small that as we keep adding more of them, it doesn't contribute too much. It does not go to infinity. So roughly speaking, I would say that as long as we're talking about series with positive terms, convergent means that the terms are small enough. That's how I'm going to think of it. Convergent means like the terms are small enough. Divergent means the terms are too big. And that's how I remember this. So keep in mind, a sub n is at least b sub n. So what this says is if the series with smaller terms, if this series is too big, and then I look at another series whose terms are even bigger, well, of course, that's too big as well. Like, if this one's too big, then that one's too big because this one's bigger than that one. That's how I remember this. Likewise, if a sub n is like the bigger one, and if the series with a sub n if this is small enough to converge, then something that's even smaller, of course, is small enough to converge. So let me give you a warning. We have to be careful how we use this. And it's important, like, which one's the bigger one, like a sub n's the bigger one, or greater than or equal to b sub n. If the smaller one converges, it doesn't say anything about the bigger one. It's possible for the smaller one to converge and the bigger one to diverge. Likewise, if the bigger one diverges, it doesn't say anything about the smaller one. So it's possible to think about the direct comparison test but not be able to draw any conclusion at all. That's one thing that I don't like about the direct comparison test. If you remember the limit comparison test, you do this work to justify using the test, and then you know for sure that the two series do the exact same thing. If one of them converges, the other one definitely converges, or if it diverges, the other one definitely diverges. But we just don't have that level of comfort with the direct comparison test. It's possible that one of them converges and the other one diverges. It depends, like, which one's the bigger one, which one's the smaller one, and so on. Anyway, it definitely has its place. For example, let's do this. So I've got a series. I've got cosine squared n over n to the 3/2. I would say this is an example of something that's just kind of begging us to use the direct comparison test on it. So in particular, or actually, I'm getting ahead of myself. Let me write down a little inequality. I'm going to kind of like get this set up. So of course, This is positive because the top is something squared and the bottom, like I'm plugging in, say, n equals 3, so the bottom's a positive number. When I say that this is begging us to use the direct comparison test, that's because of, well, partially just experience, but it's the fact that sine and cosine are always between -1 and 1. So if you see sines and cosines in a series, one idea that should jump out at you is maybe I'll use the direct comparison test. And we're just going to use the fact, basic fact, that cosine is always less than or equal to 1. Of course, that means cosine squared is always less than or equal to 1. So I have an inequality here, and so maybe I'm going to let my a sub n be this guy, b sub n be this guy. So I'm like that. And let's hope that we are in one of these two situations. Let's see what happens with a sub n. And yeah, I'm going to make a similar comment. Maybe I'll just start this at 3 because this starts at 3. It really doesn't matter, though. I could start anywhere and the answer is going to be the same. Oh, look, it's another p-series. P is 3/2, which is bigger than 1. So this series, just to be really clear what I mean, this series, because there's multiple series in play, I'm not talking about this one, I'm talking about this one. This series converges. It's a p-series with p bigger than 1. Now I hope that I'm able to use this, and I am. So the series with a sub n in it, because remember that was a sub n, that series did converge, so we are able to draw a conclusion from that. The series with b sub n also converges. So we did get our answer. I wanted to do an example where this test is actually successful, but of course, this could have gone differently, and this is one reason why I tried, direct comparison test for me, I would say, is maybe a last resort, or it's something that I use if anything jumps out at me like this cosine squared, or if I saw a sine squared. Because as we were doing this, when we got to this point, we got this p-series. If we happened to get a p-series where p was less than or equal to 1, then we would say, oh, that means this diverges, and then we would look up here and say, well, that tells me nothing about the original series. So I use the direct comparison test if something jumps out at me or if there's a last resort. But we are going to learn more tests in the future, and probably you're going to find yourself rarely using the direct comparison test. There are a few examples like the one where we just did, where the best way to do it is direct comparison test. But really, the more important one that we're talking about in this video is the limit comparison test. We're going to use that a lot more often.